Hi Gabby, I'm Chelsea. I just wanted to help you understand your homework assignment a little better. I felt really bad that I wasn't able to help you over the phone. But let me kind of try to explain it in this video for you. So the first part, and I'm going to use, looks like problem 2 on your homework, and kind of walk you through what your teacher did, and then show you with another one. So the first part of your assignment is to balance the equation. Now, what you want to do here is write out your plane equation, and you want to make sure that you have the same number of each element on both sides of the arrow. So I want the same number of aluminum atoms on this side as I do on this side, and the same number of oxygen atoms on this side as I do on this side. And the way you do that is kind of just play around with it a little bit. I'm sure there's a more legit way to do it. But I start by seeing like 1 aluminum on this side and 2 aluminums on this side. So I'm thinking let's try a 2 in front of the AL here, and then I kind of see how it works out. Now I have 2 ALs, 2 oxygens, 2 ALs, 3 oxygens. It's not really going to work. So now I want to try and even out the oxygens. So let's try 2, 3. So if I did 6, which would be like their common, like next common multiple. So we would have 3 oxygens, and then we would have 3 O2s and 2 O3s here. Then you could take this. Now you have 6 O's here, and you have 6 O's here. But now we have 4 aluminums on this side, and we only have 2 aluminums over here. So we take this and we put a 4 in front. And so now we kind of just double check and make sure all of our numbers are right. So we have 4 ALs on this side and 4 ALs on this side. Good. And then we have 3 O2s on this side. Or we have 6 oxygens on this side because you break it down into the element. So 6 oxygens on this side, and then we've got 2 times 3, 6 oxygens on this side. So our equation's balanced. So the next part of your assignment, and I kind of have some definitions up here, looks like you have to break this down into atomic and then macro. And really simple because your teacher's not asking you to actually convert it into moles, it looks like from this example. Just wants you to recognize that you can, the reason for moles is that you are able to take an atomic level reaction and pretty much do the math and get that same thing on the macro scale or the large scale. So atomic level is the very, very little bit. So it's like 4 aluminum atoms and 3 O2s gets you 1 of these, or 2 of these. And so that's kind of the atomic level. It's literally the bare minimum. The macro level is like if you put all of this into a beaker, how much would you get? So she's asking you to just recognize that you have 4 aluminum atoms and you have 3 molecules of oxygen, and this is molecules because it's 2 atoms together. And then you have 2 molecules of this whole compound, Al2O3. So 4, 3, and 2. And that corresponds to these numbers, which are the stoichiometric coefficients. And she just wants you to kind of recognize that you can go from the atomic number to the macro number by just saying, hey, this is every time I use 4 of these and 3 of these, I'm going to get 2 of these. So from there, she just wants you to look at the periodic table. And on the periodic table, you have the atomic mass number, which I'm not sure you can actually see, but it's the mass and not the actual like 1, 2, 3, 4. It's like the one with usually 2 or 3 digits past the decimal point. Either way, it's all on a periodic table, so there's nothing you need to know. No one's ever going to ask you to memorize those numbers. So, for aluminum, what you're going to do is you're going to find aluminum on the chart, and it's 26.98, and it looks like she just rounded up to 27 grams for simplicity. So 27 grams. And then that she has you saying equals 1 mole or 1 atom of aluminum. Now, if you wanted to know how much all 4 of these weighed together, that's just 27 grams times 4 m. And that is 108 grams. And that's how many are in your aluminum. Now, the oxygen, a little bit different, is 2 atoms in 1. So you have to remember that when you go and you look for the atomic mass of oxygen, which is 16. So 16 grams equals 1 atom, essentially. But you have to recognize that you have 2 atoms here. So you need to multiply that by 2. And that is going to give you the 32 that she has there. And 32 grams is going to equal your 1 mole that we have on this oxygen. So you have 3 moles of this molecule. So you're going to take now the 32, which represents just 1 O2, and you're going to multiply it by 3 moles. That's going to give you 32 times 3, 96. Perfect. 96 grams. So you've got 108 grams for your aluminum and 96 grams for your oxygen, and for your O2, and that represents the 4 aluminum atoms and the 3 O2 molecules. Now on the other side, it's the same concept, but you're going to get a different number than just 108 and 96 together, I think. No. No, it should be the same because everything should even out at the end. That's what we did when we balanced the equation. But you're going to do it based on this. So I have 2 aluminums, which was 27 grams, times 2 for down here. 27 times 2, 54. And then you have 3 oxygens, so 16 times 3 equals 48. Now, you can add these together. And you get the 102 that's there. And you can add these together because they're all part of the same big molecule here. Now you use the stoichiometric coefficient, which is 2, and you can multiply that by 2, and you will get the 204, which is the same if you add 108 and 96. So this side equals 204 grams altogether, and this side equals 204 grams altogether. And that's how you know that it's fully balanced, is that you get the same weight on either side. And that's just the general concept. Now, with the type of reaction, the only thing with that is, I don't think you have any fancy rule exceptions in any of these, so I'm just going to write, you have iron plus copper sulfate, SO4 grams, to copper plus iron sulfate. So, very simply, you don't even need to look at the stoichiometry of this to understand what's happening as far as the type of reaction. All you need to recognize is that this iron and this copper are switching spots. So when you put all of this into a beaker, you put iron into a beaker with copper sulfate, what's going to happen is this is going to break apart, and the iron has a higher affinity for the sulfate than the copper does. And so what happens is when you move this reaction forward, when you mix this all into a beaker, is this copper is going to break away from the sulfate, and this iron is going to attach itself to the sulfate. And so what you get on the other side is copper plus iron sulfate. So they kind of switch spots. And that is single displacement. You could also think about it as like single replacement or a rebound. I don't know, whatever. But it's like just the concept that you're only replacing one like part of the reaction. So like you have a cation and an anion. So a positive charge hooked to a negative charge. The only thing you're doing is switching the cation or switching the front thing. I don't want to use too many words because I don't know your understanding of that. So this would be a single displacement. Now, looking at the other one, you have on the bottom here, magnesium hydroxide. And I want to emphasize these are not balanced. They're just me writing things out. But you don't need to balance them to identify which reaction or which type of reaction it is. So magnesium hydroxide and hydrogen chloride. Nice, good base and acid reaction. So this is great. You take the same concept that we did for the iron and copper sulfate reaction, and you apply it here. You see that magnesium hydroxide and HCl, if you put them into a beaker together, the magnesium and the hydroxide are going to break apart, and the hydrogen and the chloride are going to break apart. And what's going to happen is they're going to switch spots. They're going to do a little do-si-do. And the magnesium is going to bind with the chloride, and the hydrogen is going to bind with the hydroxide, and they're going to create water. So all that's happening is you have these two things breaking apart and these two things breaking apart, and then you have this going to this to form that, and you have this going to this, and that gives you that. The important thing here is to recognize that you have two parts. You have the cation, which is the first part of the compound, and you have the anion, which is the second part of the compound. Positive charge, negative charge. Positive charge, negative charge. Positive goes with negative all the time. So if you're breaking these two apart, your magnesium is never going to go with the hydrogen because those are two positive charges. That reaction will not be favorable. Same with your hydroxide, it's never going to go with chloride. Those aren't favorable. What will happen is they'll switch partners. So think of the magnesium and the hydrogen staying put, and the chloride and the hydroxide switching places. That is, very simply, a double displacement because you're displacing two molecules. And so that's the concept there. If you have any other questions, you can text Shayla and she'll forward them to me. I stay up pretty late, so I might be around to get them. But I really hope this helps you, and I really want you to understand chemistry because chemistry is super cool, and I'm a big nerd. So I hope this helps, and I do hope you take another look at your homework. Anyway, bye!